operation of synchronous motor at constant load variable excitation. So remember here, we have kept the load constant and we are varying the excitation. So what is this excitation basically? It is the procedure or the process where we supply electricity by either AC or DC. But in case of synchronous motor, we are supplying DC. So it is the process of supplying or giving DC supply to the rotor winding, or in turn the field winding, because of which the magnetic field is produced. So this excitation can be either kept constant or it can be varied. So if the excitation is kept or it is varied and the load is kept constant, then the synchronous motor actually reacts by changing its power factor of the operation. That is, the power, even though the load is not changed there, due to the change in the excitation of the synchronous motor, the reaction by the motor or the response by the motor for this change in excitation will be reflected on the power factor. So how it is, we will discuss here. So we'll just consider a synchronous motor on which certain load is present, and the load angle is always delta. So we are not touching this load at any cost. It is going to remain same. What we are doing is we are varying this excitation. Now we have, just in case of DC motors, how we have back EMF, even in synchronous motors we have back EMF. So there we do not have something called as phase back EMF. Here, because it is three-phase synchronous motor, you will have back EMF produced because of each phase. So whenever we plot the phasor diagram, we will be taking only the phase values, per phase values, whether it is voltage, current, or back EMF, we will be taking per phase values. So we will, this back EMF is always dependent on flux, whereas in case of the DC machine, it was dependent on speed and flux. From the formula, EB is equal to 5ZNP by 60A. So EB was directly proportional to field, that is phi, and speed, N. But in some means, if you maintain this flux constant, then the only factor which affects the back EMF was speed. But here, in case of synchronous motor, that is ruled out. Why? Because synchronous motor rotates at a constant speed, which we call it as synchronous speed. So the speed is always going to remain constant. So the back EMF is dependent only on the flux. So how is this flux produced? The flux is produced because of the current which is supplied to the field winding. So basically, excitation is nothing but the current you supply to the rotor winding or field winding. By varying this, you are varying the back EMF in turn. So we are considering the operation of synchronous motor where the load is untouched, it is kept constant, and the excitation is varied. That is, the current given to the field winding is varied. Once we do this variation in the current given to the field winding, how the operation of the synchronous motor gets affected, we will see now. So first we will consider normal excitation. So what is meant by normal excitation? So you will supply the current to the field winding in such a way that the back EMF is exactly equal to the supply voltage. Again, you are taking the phase values. So the excitation is adjusted in such a way that the back EMF is exactly equal to supply voltage. Then that excitation is referred to as normal excitation. So under this normal excitation, let us consider the motor draws the current IA from the supply, and the power which is taken from the supply be P in. Now the power factor at which the motor is rotating at this condition under normal excitation will be lagging by nature. That is the basic phasor diagram of the synchronous motor, which we had discussed in the previous session. So here, if you observe, I've taken two constant lines. One is we are keeping the supply voltage constant. Remember, the supply voltage will not vary. Almost we get the constant voltage supply. So that I've drawn a constant line, or the constant voltage supply voltage line here. And there is one more component which remains constant in synchronous motor, that is IA cos phi. So what is IA? It is the stator winding current or the armature winding current, which is drawn by the supply. Now this current can be resolved into two components. One is the sine component, other one is the cosine component. So this cosine component will always be, that is, it is the component which has to be remain constant. So this IA cos phi should not be changing at any condition. So first condition is normal excitation, where your back EMF is made equal to the supply voltage, and because of that, it is the basic phasor diagram where we get the power factor lagging. That is nothing but the current IA will be lagging the voltage by an angle phi. So this is the condition, and you have to remember the voltage applied, that is the supply voltage to the motor, is constant because the supply voltage is constant, this component Ia cos phi always remains constant. So this has to be maintained constant, that is the supply voltage, and because of that, this Ia cos phi component has to be maintained constant throughout the entire variation of excitation. Now the motor adjusts its power factor. So in case now you are changing the value because of some variation, if this Ia changes, then the motor will adjust its power factor by itself so as to maintain ultimately the Ia cos phi constant. How it is, we will just observe now. The next condition, we will go to under excitation. So what is under excitation? As the name itself indicates, this back EMF is made much lesser than that of the supply voltage. Now the excitation to the field winding is adjusted in such a way that the EMF induced, that is the back EMF, will be always lesser than that of the supply voltage. So this condition is referred to as under excitation. Now we have three components here. One is the supply voltage, other one is the back EMF or the induced EMF, and the phasor sum of these two voltages will give us the resultant EMF, that is ER. Now this resultant EMF is given by IA into ZS, that is ZS is the synchronous impedance. For a given winding or for a given motor, the synchronous impedance remains constant. So because your EB is made much lesser than V now, the V is changed. So the phasor diagram also changes, because of which the resultant ER changes. So once this ER changes, this ER is nothing but IA into ZS. Now ZS is kept constant, has to be maintained constant there. So the reaction to maintain this constant or to the change in ER will be by increasing the draw of current by the motor from the supply, that is IA changes, increases. So both the magnitude and the angle of this resultant EMF shifts, because of which the IA also shifts in order to keep this component IA into cos phi constant. So under excitation condition, that is whenever the motor is under excited, the motor draws more current from the supply, because of which the power factor decreases and the it becomes more lagging in nature. So that is represented here in the phasor diagram. Supply voltage is maintained constant and it is taken as reference even now, and the load angle is remains constant, whereas now the length of this EB should be much lesser than that of your supply voltage. Now when you draw the parallelogram and complete the phase parallelogram, the resultant what you get will be ER. So the angle between this ER and I, you have to maintain this IA cos phi constant. So because there is a change in this ER, the reaction by the motor will be by drawing more current from the armature. So IA will now shift and the angle phi increases, because of which the power factor will become more lagging in nature now. And you can observe the change in this impedance angle theta as well. So under excitation condition, whenever we have the condition as under excitation, this back EMF is much lesser than supply voltage. The current drawn by the armature or the stator increases and the power factor is lagging. Under normal condition, the back EMF is equal to the supply voltage and still we have lagging power factor. But when we go for normal under excitation, it is much more lagging in nature. Next one is we'll go for over excitation. So over excitation is you adjust the excitation to the field winding in such a way that the induced EMF will become much greater than the supply voltage. So back EMF is now greater than that of the supply voltage. So this excitation is referred to as over excitation. So now once this EB is changed, you can observe in the phasor diagram, the magnitude of this EB is much more higher than the V supply voltage. Now because back EMF is changed, the phasor sum also changes and the parallelogram position shifts, due to which the resultant also changes. Now you can see just by changing the magnitude of this back EMF, the parallelogram to complete this phasor diagram changes, because of which that ER, which is the diagonal of the parallelogram, also shifts automatically. So ER is changing here, so that ER causes IA also to change in order to maintain this IA cos phi constant. So in order to maintain that IA cos phi component constant, this current leads the supply voltage by an angle phi. So during over excitation, whenever we have over excitation condition, the current will be leading voltage by an angle phi. So you get leading power factor during over excitation. So this you have to remember, over excitation, back EMF is greater than supply voltage. Current still increases, current drawn by the stator winding increases, and the power factor will be leading in nature under over excitation. The last condition is critical excitation. So what is this critical excitation? Normal excitation, we have back EMF equal to supply voltage. Under excitation, we have back EMF lesser than supply voltage. Over excitation, we have back EMF greater than supply voltage. Now, what is this fourth condition critical excitation is? Now, you adjust the excitation to the field winding in such a way that the power factor of the motor is exactly adjusted to 1. That is, cos phi is made as 1. When I say power factor is unity or unity power factor, the angle between the voltage and current will be 0. So there is no angle. Both voltage and current are in phase. So now you have back EMF in the same position. You take the phasor sum and you get ER. So here phi is equal to 0, because of which cos phi is 1, and impedance angle between your ER and IA theta is as shown. So you can observe in all the 4 phasor diagrams, we have kept this supply voltage constant. That is, the magnitude always remains constant. And the second one is IA cos phi is remaining constant. So the value of IA is changing, but this IA cos phi is remaining constant, whereas the magnitude and the angle of this IA keeps on shifting in order to make this IA cos phi term always constant. So in all the 4 phasor diagram, if you observe, you can see this IA line is always touching this IA cos phi constant line. So whether there is a change in magnitude or in the angle, whether it is lagging or leading or it is lesser, greater in magnitude, it is always touching this constant line, that is IA cos phi. So this is a very important topic which is repeatedly asked in the exam for 7 to 8 marks. So the operation of synchronous motor by varying the excitation and keeping the load constant, important question from the exam point of view. So you will have to discuss 4 different conditions here. One is normal excitation, where your back EMF is equal to supply voltage. Under this condition, the power factor is lagging in nature. Second condition is under excitation, where back EMF is lesser than that of the supply voltage. Current drawn current drawn by the stator increases, and the power factor is even more lagging in nature. Next one is over excitation, where back EMF is more than that of the supply voltage. So in this case, the current drawn by the stator is more, and the power factor is leading in nature. And then is critical excitation. So this is the excitation where you adjust the current to the field winding in such a way to adjust the power factor of the synchronous motor to 1. So cos phi is 1, unity power factor. So the phase difference between your current and voltage will be 0. So they're basically in phase. So in this case, there is no phase difference between voltage and current, and you get unity power factor. This condition is referred to as critical condition, and the value of current is minimum in critical condition. The current drawn by the motor under unity power factor will be the minimum current what motor draws under its operation. So this topic, that is operation of synchronous motor under variable excitation and constant load, is important from exam point of view. The next topic is V and inverted V curves. So this you have this topic as a part of the lab as well. We'll be conducting an experiment on the synchronous motor in order to plot these V and inverted V curves. So from the name itself, you can understand that it is basically a graph. So to plot graph, we require various values. So first we will see what are these graphs. So once we vary the excitation to the once we vary the excitation to synchronous motor, the armature current and the power factor will change in order to maintain IA cos phi value constant. So now there is a graph which is plotted between the armature current IA and the field current IF. This graph of IA versus IF is called as V curve. Basically the graph will resemble the shape of V alphabet. That is why it is called as V curve. And then the graph of the power factor, which is plotted against field current, will give us a curve which is resembling inverted V, alphabet inverted V. That is why it gets the name as inverted V curves. So remember the two curves. V curve is IA versus IF. Inverted V curve is cos phi versus IF. So IA is the armature current or the stator current. IF is field current. Power factor cos phi is the power factor. Now the circuit diagram is shown here. So it has got stator and field, that is stator and rotor. So here stator is basically star connected, and we have connected the stator to the 3-phase supply through 2 wattmeters. So this is basically, we are using 2 wattmeters to measure 3-phase power. It is a 2 wattmeter method where we use 2 watt meters to measure three-phase power. So we have connected two watt meters. So these two watt meters can be connected to any two of the three lines of this three-phase, and the third line will be taken as common. So both this voltage or terminal of W1 and W2 will be shorted to the third phase, which is taken as reference. So we are connecting this W1 and W2 to any two lines of the three lines, and then ammeter is used to measure the line current and voltmeter is used to measure the line voltage. And we have field here. This field is connected to DC supply through a variable resistance, and we have an ammeter in order to measure the field current. So what is the role of this variable resistance? So by varying the value of this resistance, we are basically varying the current which is given to this field. That is nothing but we are varying the excitation. So this condition is variable excitation. So by varying the value of resistance, we can vary the current value which is applied to this field winding, because of which the excitation also gets varied. So same thing is explained here. Stator is connected to three-phase supply through watt meters and ammeter. A 2 watt meter method is used to measure the input power. So how do we measure input power? W1 plus W2 will be giving the total three-phase power. So the armature measures the stator, or the ammeter measures the stator current, IA, and voltmeter reads the line voltage. Now, by varying this rheostat in the field circuit, we can vary the field current, because of which the excitation gets varied. And what are the readings we note down? We will note down all meter readings. How many meters do we have here? 5 meters. 2 watt meters, W1, W2. Then one ammeter connected to the line, which is reading IL. One voltmeter, which is reading line voltage. And other ammeter, DC meter, which is connected to the field in order to read field current. So we are basically noting down 5 parameters: VL, IL, W1, W2, and IF. Now here in this case, we have to note whether the stator winding is star connected or delta connected. So in this case, the winding is star connected. So in star connection, your current value reading remains same, whereas the voltage value is 1 by root 3. So accordingly, you have to change this equation. So for star connection, the line voltage and the line current and the phase current are equal, whereas for delta connection, your line current is root 3 times that of the phase current. So after these values, how do you obtain the power factor is by using this formula? Hope you remember this formula. You have done a derivation to obtain this equation as well. That is by 2 watt meter method only. So cos of tan inverse of root 3 times the difference of 2 watt meter reading to that of the sum of 2 watt meter readings will give you the value of power factor. So because we have W1 and W2, substitute this using this equation for the different values of excitation. You can obtain the corresponding power factor. So now we have what we require is armature current, field current, and power factor. The graph of armature current and field current will be giving us a graph which is called as V curve. This is how your V curve resembles. And the graph of power factor with respect to the field current gives us a graph which is called as inverted V curve. So this will be the inverted V curve what we get. This is also important. The same thing you have in your lab as well. So in the theory, when it is asked, if you write the same content what is there in the lab manual also, it holds good. But what you have to give here is what is V curve, what is inverted V curve, what is the experimental setup. You have to draw the circuit diagram, and what are the readings you note down. What will you be tabulating, you have to write. And from the obtained values, that is tabulated values, how we will calculate the required values. That is only the power factor you have to calculate. How you will calculate, using which formula you will calculate, you have to give. And then with those values, that is, you require 3 values. One is armature current, field current, and power factor. So graph of armature current, field current will give you a graph which is called as V curve. Then the graph of power factor with respect to the field current will give you a graph which is called as inverted V curve. So how to plot that along with the typical graph you have to represent.